Welcome everybody to our live webinar. I think this is episode 5. I'm joined today here by Johan Bohr, our VP of Engineering, hoping that I said that correctly.
Yes.
So
VP of Product Development.
Sorry, VP of Product Development. Morning, Johan. How are you doing?
Good, how are you?
Good. If you want to first introduce yourself, mainly what do you do here at MakerBot?
Yeah, so I'm Johan Bohr. I'm the VP of Product Development. So I oversee the product team, working on the roadmap, working on new products that come out, very closely with engineering.
Cool. And well, me, just Felipe. We've talked in the past. It's really exciting to keep you guys coming along, and do feel free to ask questions as we go along. Today we'll be talking about, a couple of very exciting announcements, starting with our brand new printer, Method X, and specifically ABS, right, which is the new material that we're introducing with Method X. We'll talk about what are the benefits of ABS, what are the kind of ABS formulations that we see out there, because it's, there's a big disclaimer usually in 3D printing when talking about ABS. And ultimately, what are the features of this printer that make ABS printable or possible to print with our Method platform? So with that, we'll get started with the deck. Oh, and also remember, Alison and Mateo behind cameras, kind of capturing all the questions. So if you have questions, do ask them out in that. I think it's in the right hand corner, and we'll be addressing them as we go or at the very end, depending on them. So as you guys know, we've been around for over 10 years now. It's been quite a road, starting from the cupcake 10 years ago, and slowly evolving that platform that very much emerged from the hacker, sort of more makery spaces, right?
So MakerBot pretty much pioneered desktop 3D printing. And as you said, the cupcake CNC in 2009 was really a very groundbreaking product, because previous to that, 3D printers were really tucked away in like labs, and it was not accessible. So that was really bringing 3D printing to the forefront. And since then, we have evolved quite a bit. The first printers were kits that you had to put together, right? So we came out with printers that were pre-assembled, like the Replicator 2. And then from there, we evolved to really advancing the user experience and adding connectivity to the printer, making it very easy to use. But, as with any platform, at some point, you kind of hit a wall in terms of performance and how far you can go. You can make it a little bit better, but I think especially for desktop 3D printers, there's still a big gap compared to industrial 3D printers when it comes to some of the performance aspects, such as the reliability, the dimensional accuracy. In the professional environment, a 3D printer really has to be a tool that you can rely on. That when you hit print, you get the result that you need, and you can move forward in whatever or with whatever you're doing.
Right.
So the experience with a lot of desktop 3D printers is you can somehow get to a result, but oftentimes you need to tinker a little bit. You need to kind of babysit the printer. And as you do that, you lose a lot of time.
Right, and that's interesting because we hear that a lot, especially like last year we introduced our Method platform. So as Johan was saying, it's like trying to bridge that gap, if we go to the next slide over, between desktop and industrial systems, right? Getting the best of both worlds. And many people were saying that, I can get really good results if I spend the time in my machine. I can set my machine to actually print really nicely. And what we're trying to do with this platform is mainly allow you to just print, right? It's a different experience.
Yeah, so I think a lot of customers that we talk to, sometimes they have access to an industrial 3D printer, but they have to get in line, they have to, it's very cumbersome, and it takes a long time for them to get access to the printer. So they start buying desktop 3D printers, but that to a degree is not scalable either, because oftentimes the managers don't want you to waste half of your day trying to get the printer to work or get the result that you need. And so the idea behind Method really was take some of that industrial technology from Stratasys and put it into a very accessible form factor that an individual engineer can have right next to them, with a similar reliability and a similar overall experience and result in terms of the part that comes out of the printer.
Right, and it's what we see right here in this chart, right, where we're taking the best of both worlds. So starting with the precision and the reliability of industrial systems, but as you say, it's like usually gated by a technician. It's not that, I'm an industrial designer, so me as an industrial designer, I couldn't just walk to the printer and print. But in the desktop side, we have something that's very accessible. I can have it by me in the desk and just hit print. But I won't necessarily have that reliability. It's easy to tinker with, and I'll spend time on it, but it's not just a tool that I'm continuously using.
Right, and so what really that meant for us is that we had to go back to the drawing table and say, let's start from scratch. What do we have to do or how can we like design a printer from the ground up if we just ignore everything else and say, how can we make a printer that is very close to the industrial technology? And in that process, at MakerBot, we were very lucky because Stratasys is our parent company. So we have a lot of resources and knowledge that we can tap into to say, what did you guys learn? What are some of the technologies that we can use to develop a completely new printer? And that's why it has taken us quite a while to come out with this printer, but now we have a completely new platform that's very different from anything else that's out there.
And this is actually, if you guys can see it here, but this is it, right? This is the Method X, the newest model of the Method family. And as you're saying, it's the Method family as a whole is the first full-on sort of line of products that came after we started working with Stratasys, right? So there's many of their IP reflected on this platform.
Correct. So the biggest feature really of the Method, I would say, that contributes to the industrial nature and the dimensional accuracy is the heated chamber.
Right.
So with desktop 3D printers, they usually have a heated build plate. So you control the temperature on the first layer, and that can reduce the warp that you get. But as you move down in the build, in the Z, you move further away from the build plate, so then the temperature changes. And with plastic, it's very important that you control the temperature at which it cools down. Because if you don't do that, you introduce defects, you can get deformations, and then also ultimately your part is not going to be as accurate. And it depends on the material that you're printing, but with Method X, we're printing ABS, and we're going to talk a little bit more about that. For ABS, this part is very, very important.
Right, and we've seen that a lot especially many desktop printers that offer maybe larger print volumes. The larger the print volume, the more important it is to actually keep constant control of your print environment, right? It's more prone to have those deformations happening.
Yeah.
So let's talk a little bit about the heated chamber, and then it's kind of one of the key differences between Method and Method X, right? So both of them have the heated chamber. Is that correct?
Yeah, correct. So both of them have a heated chamber. The difference is like how hot can the chamber get. So with Method, we go up to 60 C, and with that we're printing PLA, we're printing TUF, we're printing PETG. But if you want to print true ABS, you have to go higher. So Method X, the chamber really goes up to 100 C, and that allows you to print true ABS very successfully and dimensionally accurate.
And you keep saying and we'll elaborate on the heated chamber, but you keep saying this like true ABS, right? What do we mean by that?
So desktop 3D printers, like I said, use a heated build plate to reduce warp, but they also modify the ABS so that it doesn't warp as much. So they basically add modifiers to that, and if you do that, then you're also sacrificing some of the qualities of an ABS. So in terms of strength, in terms of heat, deflection temperature, you're not going to end up with the same kind of properties. So what you're printing really is not a real ABS.
Right.
And they do that, of course, because of the limitations. Because like I said, if you print a real ABS, you have very high shrink rates. So you need to make sure that it cools down gradually and slowly to avoid the cracking and the deformations. And that's really the benefit of the heated chamber, that you control the temperature at the build plane. So wherever it's at the build plane where the printer is printing, you're controlling the temperature. And then as the build plate moves down, it cools down gradually.
So in this, a part long as this one, it's more important, to keep the temperature constant, because you're really like a good 7 inches away from the build plate at the point that you're finishing the part, right? And the other thing is that I get asked a lot is in Method X, it's not just a software change. Those 100 degrees actually come with a quite robust set of different electronics on it. So the heaters are different, right? And the electronic consumption is different as well.
The heaters are different. Electricity that we provide, we need a bigger power supply to power those heaters.
Yeah, I have a few stories about us popping the... So we've run a few of them here. You have to be careful about how many of them you plug to a single outlet, because they'll run at 7 amps, a little bit over 7 amps, and 800 watts, right? We were printing on them. If you have enough of them on a single outlet, well, you then have a fun conversation with your facilities manager, because it is a much more robust system.
It's that, but it's also that the bellows that kind of sit above the extruders, those we added an extra set to keep the heat inside of the chamber.
Right. Yeah. So, and now let's talk a little bit more about, we've mentioned ABS a lot. Hopefully, you guys are familiar with it. Basically, it's a plastic that Legos and many of the things, I would say like probably over half of the things that we interact on a daily basis that are plastic are probably injection molded ABS, right? So ABS is just, I won't try to say it because, I'm not that good with chemistry, but it's an acronym for a type of styrene, right? It's a thermoplastic, similar in some ways to, your PLA, your PETG, but it has some very specific functionalities, which makes it amazing for injection molding, right? And it's amazing for industrial processes.
Yeah, so typically, one of the main reason why ABS is so popular is the combination of strength, durability, and also heat resistance. So you get a really nice mix that lends itself very well for most of these applications.
Yeah.
And knowing that most of the injection molded parts or a good majority are made out of ABS, it's of course very beneficial to be able to either prototype or produce and use parts in the same material on a 3D printer.
Because what we hear a lot from many engineers is that they want to be able to prototype on the material that the part is going to be manufactured, right?
Correct.
So if you're using ABS and injection molding as your final manufacturing method, the closer that you can get via your prototype, it being in ABS, the better, right?
Correct.
So as Johan was saying, ABS is used a lot in different applications. So you can see, like in this next slide, all of the range of applications that you see in your kitchen, even, right? Just home appliances, anything from the housing in your iron. If we go to the next slide over, all of the base on the blender. Basically, half of the coffee machine is also ABS. So most of those really shiny plastics that surround us everywhere are going to be ABS, right?
Yeah, correct. So, yeah, like you mentioned, it's a vast majority of products, and especially when you prototype, you're trying to mimic the final product. So it's important not only that your dimensions are similar to the final product, but also the properties of the part and the material that you're printing with. So especially when you're doing functional testing and you're trying to test the functionality of the part, you want to get as close as possible to the properties of the injection molded part.
Right. So moving along on the specific, technical difference between desktop ABS, the range of ABSs that we've seen out there, and method ABS. There's a few kind of key categories that we found where ABS is really different. The formulations are different between what you would call your industrial grade ABS versus the formulation that happens for most desktop printers, right? So we've grouped them in 3 big categories. As Johan was saying, it's like about strength, then heat resistance, and then finally the types of support that you can use to actually print. So let's start with strength, right? What are the difference between ABS, like production grade ABS, and the desktop ABS?
So first I want to mention that this testing is based on injection molded parts.
Yeah.
So it really shows the properties of the polymer itself. When they're 3D printed, it's a whole different world. We think that the difference is going to be even bigger when it's 3D printed because of, and we're going to talk about that later, because of the way the heated chamber impacts, for example, layer adhesion, so that the layers bond much better within the heated chamber and you end up with a stronger part. But even like on the injection molded part, when you just look at the base polymer that's used, because of the impact modifiers that desktop 3D printers add to the material, you're impacting some of the qualities, and you're getting, pretty far away from what you would get from an injection molded ABS. So in terms of the tensile strength, you can see it's a 12% difference between the desktop ABS and ours. The tensile modulus, which really talks about like how stiff the material is very different. And the heat deflection temperature, which is one of the key things that you want to get out of an ABS. You want to get a material that can withstand the heat, because otherwise, other materials have lower heat deflection, like PLA or TUF or even PETG. PETG is a little bit higher.
Yeah.
But so if you don't get those qualities from the ABS, then you're making a lot of trade-offs.
Yeah.
So yeah,
it's
those are, I
interest-
think, the key things. But the last
Yeah.
piece that you mentioned is the support material.
Right.
That's a very, very important one.
Right.
You know, one of the key features of Method is that you can print with soluble supports.
Mhm.
So you have full geometric freedom. You can print very complex parts. You can
Mhm.
print parts that have grooves, that
Mhm.
have holes, that have maybe structures inside of the part where you wouldn't be able to remove any breakaway supports.
Yeah.
So that's a key benefit. But the problem is with ABS, you know, you need to find a material that bonds with the ABS,
Mhm.
but then also one that can print within the heated chamber. Because if you
Right.
use something like PVA, you know, that cannot withstand the high temperatures. And so even on a desktop 3D printer, for ABS, most printers only offer breakaway support, so you're
Right.
limited with the geometries.
Uh-huh.
Or they offer maybe PVA for smaller geometries. So what we're using is called SR30.
Right.
And SR30 is an industrial support material for ABS that was designed by Stratasys specifically. It has some of the similar ingredients as ABS, and
Mhm.
what that does is that it bonds very, very well with the ABS. So you get very reliable, very reliable prints and very good surface finish.
Mhm.
But then also it has the heat resistance to print well within
Yeah.
our 100C chamber.
So that's one thing that we've seen too, right? In this case, I have two prints with me. One of them is this red one was printed on a Method, and this black one was printed on a desktop printer. So starting by the fact that on the desktop printer, they only allow you to use breakaway supports, right? So removing the supports here is going to be a manual process, and sometimes, especially with a part that becomes as complex as this one, you know, once I remove the supports, you can see that the part is fairly complex, right, altogether. So removing those by hand, it's going to be quite a painful experience. And not only that, but what you were saying is that also you can see, you know, we would need to be really close for this to happen. But what I can show right now is like the layer addition. You might not be able to see it right away, but in the part, there's a lot of layer delamination. We'll have a photo of it and coming up. But the thing is, most of engineers, when we talk to them and they ask for ABS, right? Because we've been hearing this since the Replicator Plus days. They want ABS because of the strength that it gives you, right? You want to prototype something that will withstand certain loads and certain pressures. But with desktop printers and with desktop ABS formulation, you're not getting that strength that you're looking for ultimately when using ABS. So we'll come back to this example in a second, and I'll show you what I mean by the layered lamination, because it's actually really impressive how easy it is and how brittle the parts become because of the fact that the layers are not bonding appropriately. So if we keep moving into our deck, yeah, these are the two. Just one before. Sorry, the two tests that we ran with our parts, starting with the strength test with the ASTM. So is it American Standard of Technical Materials? The acronym. And basically what we're doing is pulling away the plastic in one and then pushing into it, right? If you want to talk to on those tests a little bit.
Yeah, so the tensile strength test is a very common test used to test materials and compare the strength. So essentially what you do is you create a little specimen that you can see in the middle there, and you pull it apart to test, you know, when does it fail. And on the right side, the heat deflection is showing when does that part deform under a certain load.
If it's heated up.
Yeah.
Right.
So at what temperature?
Uh-huh.
At what temperature does it deform?
Okay. And in both of them, our the actual standard ABS formulation is way better than the traditional desktop formulations.
Yes,
right?
correct.
Like 10 to 20%.
Right.
Cool. So if we, keep going. So this is what I was talking about in layer delamination, right? You see like the two parts side by side. One is a Method X print. The other one is a competitor print. And it's very similar to this one. And I'll show you what happens. I'll show you what happens when you actually have both parts, right? So this has the same, very similar defects to the ones that you're seeing on your screen right now. And the thing with those is that if I pull, you can probably hear it in the mic. Shout out to Natalie who likes ASMR stuff, but right? Ish, I mean, it's kind of crazy. I'm strong, but I'm not that strong. Right? I shouldn't be able to pull apart. So, wow. So, I mean, the layers are so brittle and so far apart that it's so easy for you to pull apart off. And here I have another example. This is, in this case, a method part, right? It's one of our housing, and it's, even if I, I mean, this is what you're looking for, right? And it's a way smaller part, and even I'm starting to sweat already, but it's just never gonna happen.
Right, and I mean that. Again, this has to really to do with the heated chamber, because the layers, the plastic basically stays at a higher temperature for a longer time. It stays softer, and so those layers can really bond together and become one and become very strong. Yeah. Versus here, where they cool down very quickly, so then the individual layers don't bond together as well. Yeah. And that's when you get these kind of this kind of like delamination in here, where you can like very easily just peel it off, basically, right?
Yeah, it's crazy. I mean, I'll try to bring it closer to the camera, but like this is the one that I pulled off. It's just one of the layers, right? But you can see that it's already also happening in other layers right here, and that's just because the ABS is not bonding consistently throughout the part. So that's for some of the more technical members of our audience, it's basically anisotropic materials that don't behave the same way when the force is applied in one direction versus another direction. So, just because of the way that 3D printing happens, you will have a different structure in the Z direction versus in the X and Y, which is why it's really important to control layer addition and bonding throughout your part, not just in some of them, right? Here we have another example that we used in-house right here. So you're seeing a heat gun that we're using to clean up some of the prototypes here. And basically what we did is we printed the nozzle. And the same story is true, right? So I have, let me bring it here. The first nozzle that I print, so this is a method nozzle if you want to hold that, Johan. And this will be like our desktop nozzle, which as soon as I took it out of the machine, it started to break apart. And I'll try to do it again, but it's just crazy how easy it is to just push and pull on the part, and it just snaps, right? Because each layer is not going to have enough addition between or into the next layer, whereas if I take this one, I mean, I wish there would be a way for you guys to feel it, like to trust on the back to pull on these parts, but it's just impressive how easy and the immediate difference that you get between one part that's been printed appropriately with a heated chamber and controlling each layer, as opposed to something that I can break apart with my bare hands. Also the fact that this part needed to withstand temperature after the fact, right? So we see that also in many engineering applications, parts that need to withstand heat. In this case, it was a heat gun, so it doesn't go that high, but it's high enough that you'll need a material that can actually, touch that nozzle and not be melted away. And the next example that we have right here is basically talking about, the tolerances and the specs that we can respect. So as we've mentioned before, one of the reasons why ABS requires a heated chamber is because it's going to shrink, right? Let's talk a little bit about shrink rates and ABS. It's just a property of the material that you have to work with, no matter what. Is that correct?
Yeah, that's correct. And so if you don't control how it cools down, you get higher shrinkage. And if you have a part like this that's part of an assembly, right? The parts are just simply not going to fit together.
Yeah, so that's really important. I mean, it's important in most applications, but when you're trying to do a functional prototype like this one, just want to trust the fact that what I design in CAD is going to be what I'm getting out of the printer. And that's something that we hear a lot from our users, right? This idea of design for 3D printing, where many times when people are using a desktop printer, they'll have to accommodate for the different tolerances of the machine, right? And that ultimately just adds time, which is valuable time that you'd be better off spending on iterating on the model, as opposed to making sure that the parts are going to fit. Like in this case, we have some inserts that needed to go into that part. We have the little holes here that had to match between the two halves of the part. So in this case, it's a pneumatic pump, right? You have the impeller in the center. I'm sorry if that's too noisy on the mic, probably. So the impeller in the center and the external housing, right? Everything had to fit together. and there was no change because I actually printed this one myself. We didn't change anything on the CAD itself to make it fit. It would just right of the machine, it fits, and I can keep on working and keep on iterating.
Right, and so on our end, we do spend a lot of time measuring the dimensional accuracy. Both our engineers and the manufacturer, everything that comes off the printer, we have a very big number of printers running 24/7, printing parts, and then measuring every part and tuning and making sure that we hit those specs that we need to hit, which is 0.2 millimeters or 0.002 per millimeter of travel. So that's a spec that is very similar to what you would get from injection molded parts. So again, it's not just like the properties of the material that's similar to injection molding. It's also that the dimensional accuracy is very, very close. So when you put those two together, if you do this kind of functional prototype, you're going to get as close as it gets to the final product that's going to be injection molded with a prototype that was 3D printed, which you can produce much faster, which you can produce at a lower cost. And so overall, this really will accelerate your development of products if you're talking about prototyping, or even better, with all of this, you can also produce end-use parts. Parts that, like you mentioned, like this piece that you use for the heat gun, that you can actually use. Whether that's like in a manufacturing environment or that's a company that has very small quantities of very customized products. With this printer, you can produce those end-use parts.
And we have a few examples that takes us nicely to the core applications that we see specifically for Method X, right? We'll come back to Method in a second, but for Method X, you were talking about the three main ones, right? Functional prototypes, then manufacturing tools, and finally end-use parts. So let's talk a little bit about each of them, starting with functional prototypes. What do we have here? And it's the same part that we've been touting around during the webinar.
Yeah, so this is basically a functional pump assembly. You already talked about this a little bit, but essentially it's a prototype that a company would print this out to kind of test this design. Maybe they have multiple designs that they want to kind of figure out which one works better. To be able to have this part be so close to what the final product will be in that test makes that test more valuable. And why do you do that kind of functional testing is so that you reduce the risk of finding some kind of design flaw once you go into production. That's kind of like the overall goal of this. But also, by being able to quickly print multiple designs, you can do this kind of functional testing and see like how do these different designs perform, and which one is the one that you should further advance and iterate on. So again, this is like all about speeding up the product development with getting a prototype that is as close to what you would get. And like you mentioned, so there are multiple aspects to like dimensional accuracy. It's the dimensions of each of these parts so that they fit together, but then it's also things like the cylindricity. So that means how round is this hole? So if you have an insert here, basically this hole needs to be made together with like a pre-existing part, like a screw. It could be maybe like a magnet insert. It's important that this matches exactly what you put into very CAD. Closely to what you put in the CAD program. So you don't have to print this out 10 times to kind of find an adjustment that maybe at some point works.
And an interesting thing that you mentioned is like you may want to just the fact that you're able to iterate quickly in CAD, especially nowadays, right? You have many parametric software that you're able to just change the number of ribs here. It's not a rib, but the blades in your impeller, and in 5-10 seconds you have a completely new CAD design. So being able to have a tool that matches your speed in CAD is also really important. We have a lot of plugins that also connect directly to your CAD programs and enable you to have that free interaction between digital and physical prototyping, right? Moving along to the next application now, we have the manufacturing tools, right? So let's talk a little bit about this one, which is quite a kind of a crazy looking big thing.
Yeah, so just as some background, like manufacturing tools are basically aids that are being used to manufacture products on the assembly line. Traditionally, most of these parts were made out of metal, so there's a long lead time. It's very expensive to produce them, but more and more manufacturers are replacing some of these parts with 3D printed parts, and that could be anything from something that holds something on the assembly line, something that is like a functional tool that performs a function, to maybe a gauge, that is used for quality inspection. If once your parts come off the assembly line to make sure they're in spec. So many different versions of manufacturing tools, but what all of them have in common is that the manufacturing environment overall is pretty harsh. Things are being beaten around, they're covered in oil, like the conditions are harsh, so you need a material that can withstand that. And like I said, that's why a lot of these manufacturing tools traditionally are made out of metal.
Right.
And the more of these parts you can replace and 3D print, the more money you're going to save, the quicker you're going to improve your manufacturing process, and the more agile you're also going to be in reacting to things that maybe some of the engineers or the people that work a line see that could be improved.
And let's talk about these
Let's
parts
talk about this part specifically, yeah.
So what do we have here? I mean, it's kind of a weird bunch of tubes and rectangles here.
Yeah, so right now we're working with a company that focuses on factory automation. So one of the big trends in manufacturing, obviously, especially here domestically, is to automate the manufacturing as much as you can so that you can compete better. And so what's being used for that are robot arms. They can perform a lot of the tasks on the assembly line. And so what we're looking at here is actually a sanding tool. So on this side, this tool would attach to the robot arm, and then you have sanding pads on each side. So this device could perform like a sanding. It could perform a sanding application.
Right. So you have basically the hand coming in here, and then this is like a port for the vacuum. Is that correct? Like where you can, all of these ports are actually sucking the sandpaper, right?
Yeah.
Not sandpaper, the debris
dust,
from the sanding process. So you can sand with one. They were using two different sides because they wanted to use two different grades of sandpaper, right?
Yeah, correct. And so again, this is what's called an end effector for a robot arm, because it's basically the piece that goes to on the end of the robot arm. So there are many different tools. There could be a gripper, there's like pick and place operation. This obviously is a sander. The reason why we like this part, and the company that we were working with was very excited about this part as well, is because it's something that is very complex that you can't really machine in this geometry. And it really needs to have dimensional accuracy so that it really fits onto the robot arm. If you don't meet those dimensions, it will not fit. It also is very complex because it has all these carve-outs here, so that you need the soluble supports to be able to print this kind of geometry, because you can't, it's impossible to put breakaway supports inside of here.
Definitely. You would never be able to get it out.
Right.
And then the final example that we have here, actually, I took the Raspberry Pi out, but it's basically an electronics housing, right? So we have the Raspberry Pi here, and we have the housing for it. Why would somebody, prototype this type of component?
So this is like an end-use part. So there could be a company, for example, that makes a small quantity of very specialized inspection devices, and because it's such a small quantity, let's say 100, to like injection mold it and tool it up would be extremely expensive. So a small quantity like this, if you need the housing for it, you can 3D print it on the method, and you print it in ABS that can withstand the heat. So, for example, inspection devices, sometimes they're being left outside in the car. It gets very hot in there. If you print them in something other than ABS, like a PLA or something, they would probably melt away, and not melt away, but they would get damaged.
Right, it probably would deform.
It would deform, exactly. So for something like this is a great example for a company that could produce a small quantity of end-use parts, where 3D printing offers you a much more cost-efficient and also faster way to do this.
And for this one, we also have, you hand me that one over there, the example printed on a desktop machine, right? So it's the same idea. Both, it's the same part. But again, I'll bring it closer to the mic because we've been playing with it a little bit, but right? I'm just like pulling it a little bit, and it immediately shows. And let me bring the red one. I mean, it's just it's interesting to see, like, it's the same part and completely different performance out of them. So moving along, let's talking about what are the key elements that. Oh, we have a final example. Sorry about that. So we've spoken a lot about the Soluble supports, right? And in this case, we have a great 3D print. It was designed by one of our designers here, Andrew Askedal. It's a very complex assembly, right? It's a gripper example. And we have it printed on a competitor machine, a desktop system, and a method, right? And what happens is if we go to the next slide over, you'll see that once we dissolve the supports, so in this case, they were both using PVA, the method one is able to just, smoothly move. And on the desktop one, the parts just fuse together. So if we go to the next slide over, you'll see in the close-ups that what's happened is that the gears are completely melted together because it's that lack of control. It's not only affecting the way that the plastic is going to shrink, but also how the plastic is flowing out of the extruder, right? So you're not able to respect the tolerances between the two parts, hence the assembly just fuses together and it's ultimately unusable. Yep. Okay, so let's talk about some of the systems that comprise the method family, both method and method X, because they do share a lot of these systems, right?
Yeah, so I think we talked a lot about the heated chamber, which obviously is like a big part of this printer. But as I mentioned before, this printer was redesigned from the ground up, so there's a lot more than just the heated chamber that makes this an industrial 3D printer. So, it starts with the frame. It's a very stiff frame. I think we're going to go over some of this.
Yeah, we'll go through the features, but like starting with the key difference between both of them.
Right.
So they print in fairly similar materials. Both of them start with your basic PLA, your tough, also PETG now that we introduced earlier in this year. And in the case of Method X, as we said, ABS, right, which comes with the SR30 soluble support. And both of them are also able to print with PVA, which is water soluble. So not only soluble, but just dunk it in water and you get rid of the supports as easy as that.
And, I also want to mention materials for this platform, for the method platform, are a very big priority for us. So, just this year we added PETG and now ABS and SR30. So we're working really hard and very fast in adding new materials, so there's a lot more to come. And as you mentioned, I think that when you decide between these two systems, you shouldn't only decide between like ABS and the materials that we offer on V1, but look at the chamber temperature and look, like, do you need higher temp materials? Because eventually this machine with the 100C chamber will be able to support other more industrial materials. So it really depends on what you're looking for. I think that for a lot of applications, tough material, PETG and PLA is perfect. So maybe you decide you don't need ABS or any higher temp materials, and then this printer is good for you. That's especially true if you're mainly prototyping.
Right.
You just want like quicker concept models. You're doing some fit tests. Once you go more into like functional prototypes and end use parts and manufacturing aids, then I would highly recommend that you get the Method X. Because of the ABS and also as I said, the potential to support other higher temperature resistant materials.
Right, and what you have there, just to double click on that comment, it's the key difference in the heated chamber, right? You see it there, it's 60C and 100C, and there's a actual mechanical or systems difference between the two of them, right? So one of them runs at 400 watts, that's Method, and Method X that runs at 800 watts, so twice the amount there. And also the power requirements in the amps are quite different in both of them. As I said, you probably will want to keep that in a single outlet, but it's a different system that allows you to go way higher. And going into the shared features, so starting with the ultra rigid frame, I think it's coming up on the next slide. So that one was one of the first things that we introduced with the method, right? We wanted to create a platform that was really stiff, and stiffness is great to guarantee dimensional accuracy.
So the stiffness, so you can imagine the more flex you have in the system, the more everything is going to move around. And so what that means, as you extrude, there's going to be some wobble. And eventually that ends up in the printed part. So with the stiffer frame, we get very good vertical layer alignment. So if you look at this part, you can barely see the layers. It's very, very smooth, the surface. With a desktop 3D printer, you don't really get it to this degree. The layers will stick out more, and you have more resistance on the surface of the part. So that's one of the key features of an industrial 3D printer. It's just the frame. And that's also where some of the weight of this machine also comes from, that will give you a much better vertical layer alignment and ultimately like surface finish of the part.
Right. And now talking about and the next one over, it's the Soluble supports, right? So starting with SR30, it's dedicated support in this case for ABS. It's just great to make sure that your part adheres to the support, because ABS really doesn't want to play along with many other materials, right? And you were saying like this was originally developed by Stratasys, which is why we have access to it.
Correct.
And it's water-based removal, but you have to use a different system with tablets, right?
Yeah.
It's basically changing the pH of the water.
So Method is the only 3D printer in its price class that has these kind of soluble supports, the SR30. And yeah, like you mentioned, for this one, you use what is called EcoWorks tablets, and you need agitated and warmer water to dissolve it. But other than that, it's very simple. And like I said, because the SR30 has some of the same ingredients as the ABS, the bonding between the two and the printability of the material is very, very good.
Right. And then the next one over, the next type of support material will be PVA, which is shared by both Method and Method X, right? So it's going to be something that's entirely water soluble, as we said before. That one, you just place it in water and you're good to go, right? It's nothing else, nothing added to water, which is great for an office-friendly setup, right?
Yeah, so I think that for any like quick prototypes that you need, the PVA really is the way to go. Like you said, it's water soluble. It really doesn't only take agitation. You don't need agitation, but agitation will speed it up. And the nice thing is that the Method X supports all of this, so you can switch between those different environments. Like if you're just doing like a quicker fit check on a prototype, you can print with PVA and tough. If you produce like an end-use part, you can switch over to SR30 and ABS.
And one of the reasons in the next slide over is going to be, one of the reasons that why we were able to print with both supports is because we have two extruders running along, right? So it's dual performance extruders. And basically that means we're running two extruders, one with model material, the other one with support material. These extruders were also developed from the ground up. It's way higher torque so that it can really push the filament through. And also controlling the rate at which the material is being extruded much better, right? Because it has a longer
It has a
core.
longer thermal core, and so that allows us to also print faster, simply because it can melt more of the plastic at once than the thermal core of a desktop 3D printer could. We're also not there yet in terms of even maximizing the speed, so there's still room for us to even optimize it more. We're already faster than desktop 3D printers.
And it's improved a lot.
It has improved a lot.
Because when we first launched Method, it was like kind of the big number was twice as fast, which we proved. And now I'm getting results where it's almost 3 times as fast. Just because in ABS, what happens with many of your desktop machines is that they will slow down the speed considerably. Because if they don't, then again, the ABS wants to contract quite a bit. And in that speed reduction, there's a huge increase in print time, right? Which doesn't happen with Method. So the next feature over is going to be our material base. So you can see here, our materials are not exposed. They are constantly enclosed inside of the machine, which is really important, especially for these water-soluble supports, because of the fact that they'll soak humidity from the environment.
Yeah, so we control everything about the material. So it comes in a dry sealed bay that has a desiccant built into the spool.
Right.
And then once it's in the bay, these have a seal here. They have a moisture sensor inside the bay so that you can make sure that it doesn't absorb too much.
Yeah.
And that is important because, like you said, the PVA is water soluble. So it absorbs moisture even from the air if you leave it out in the open.
Yeah.
And then what happens is, like, when that moisture gets into the extruder, you have little moisture bubbles. They explode inside the extruder, and then you introduce all kinds of defects into the print. So the more we can control that, like we do with Method, the cleaner your prints will come out.
Right. Next feature over is going to be just the fact that we've tested these machines thoroughly. I think we should update these slides because we're now at close to 300,000 hours.
Yeah, if you take all the testing that's been performed between Method and Method X, we're at 300,000 combined, and that includes the printer testing, subsystem testing, some of the engineering testing that we've done here, plus what our manufacturer also does.
And the beta users that we're using, right? So
yeah, that's not even included in here, but yeah, we do have a good group of beta testers that tests each machine.
So if you want to get a free machine, email Johan, he'll set you up with one. No, but it's great to see like actually real results from many of these industrial applications and see people that are super happy with the results already. Let's see, and I think that sums it up. All about the systems for now. We've talked about the ABS, our brand new Method X, and I'll open the floor for some of the questions that we have through the chat, and feel free to add more, and Alison will be bringing them up.
Let's see. Do you have any statistics on the UV resistance of real ABS?
Right. So ABS is not the best material that you will want to use for UV resistance. For that, it's better to use PETG. PETG has if you're looking for something that's going to be outdoors, exposed to the sunlight, PETG is a better material for that. I don't have the exact number, but I do know that it's more sensitive than PETG. So we have both options, which is great. You now can choose. ABS is better for those high strength parts, the higher heat deflection parts, and PETG is better for when you need chemical resistance, because ABS is a little bit less. It's not as good as PETG for that application, and also for UV, basically exposing your part to sunlight, it's probably going to be better to use PETG, which we also offer for Method.
Do you find that the method printed ABS is as workable as normal injection molded ABS? Does it drill well without fragging a part, for example?
Right, so I'll repeat the question because I usually get scolded for that. Is the method 3D printed material as good as the injection molded ABS for drilling and maybe post-processing? The answer is yes, it's actually really solid, and we also offer a full solid mode. So, I'll take this part again. This is not a part that was printed on Method, but showcases what happens with many of the desktop systems that will have a lattice structure inside of the part, right? With Method, you're also able to choose solid mode, which is going to be, a little bit slower, of course, because you're adding a lot of material, but it will behave much closer to what you would expect to an injection molded part. As I said before, injection molded parts don't have that Z component that will always be present because of the manufacturing method, but it's really close. And yeah, we have drilled with Method. We have some of these parts. We had to add the inserts and whatnot, and it's not it's not deforming as PLA that just sort of explodes. Yeah. We also have tough if you want something a little bit more chewy, but that's a different story when we talk about more of the materials that we have available for Method.
What is the life expectancy of the extruders compared to the Rep Plus, for example?
Okay, what's the phrasing the question again? So life expectancy of the extruders compared to the Rep Plus. I think that they come for the warranty is for 6 months.
The warranty is for 6 months, and there's overall the life of the extruder is much better than on the Replicator Plus. I think that for the model extruder, I think it's somewhere between 600 and 800, and I think for the support extruder is even higher. It's 1,000 plus.
Yeah.
Great.
Hours.
When will it be added to the website, and when will we know consumer prices?
Oh, it's on the website right now. So if you go to makerbot.com/method, sorry, we may have we'll promote it a little bit more, but it's on the website. So if you go method.com/method, you see both prices, and we actually just now, since we introduced Method, we dropped Method X, we dropped the price on regular Method. So now regular Method starts at $49.99, and Method X is $64.99, right? So it's quite a good deal. It's a printer that's under 5K. That's really close to most of the desktop systems with a much it's just a beast of a machine, even Method. It's right on the website. I would encourage you to go there, and I'm sure that our demand gen director, Julia, will appreciate that. So Method, makerbot.com/method.
And it's not available for purchase on the website yet.
It is today, starting today. So yeah, starting today, we're actually going to start the e-commerce sale. So we started offering, so we added it to the website 2 weeks ago when we first launched. And just today, we're going to open the e-commerce side of sales. So you'll be able to just buy it online, whichever one you choose, either Method or Method X, at the click of a button. There's also credit options with Affirm. So kind of, how do you call it? Like payment? Financing with Affirm. So that's also a great deal. You end up paying I think less than $200 a month for the machine, which is great to outsource, the price of it. But yeah, it's going live today on the website for a store.
Related to that, is ABS available on the website? And if so, when will it be released?
That the answer is the same today. So today we're adding a lot of things to the store. We hadn't done that because of the fact that we wanted to make sure that we had enough stock. We have a very good demand for Method, and we wanted to make sure to guarantee the demand on the store as well. But today we'll add Method X and the ABS spools on the store as well.
Great. Will a MakerBot wash system be available for SR30 support?
So the question is, will we add a Method wash system?
So currently there are third-party solutions that we recommend. There's actually a document. I'm not sure if that's on our website yet. I think it's in our support page where we recommend 2 different systems that we have tested here internally. As to our own solution, it's something we're looking into. I can't comment more like on our roadmap and what's planned there, but we're definitely investigating it.
Yeah.
Cool. Let's see. Would you ever consider publishing a development schedule so that the customers know when things are coming?
Yeah, that's especially for materials. So I'll rephrase the question. Publishing a development schedule. I think that right now, as we have a more, a clearer understanding of the materials roadmap, would be something that would be really interesting, because we hear that a lot from our customers, especially when you're committing to a system. You want to know what's coming. And the interesting thing here is that with many of these machines, they grow, right? It's not you're not just buying one machine at that state, but actually we are constantly adding features to it via software updates or new materials, like what happened with Method.
Right.
So we launched Method in December last year, and then by March we already had added a new material, PETG. Now with Method X, the same is expected, right? So we'll be adding more materials.
I think overall, once you tackle a certain chamber temperature and you're able to print at that temperature, it opens up a new world of other materials that maybe print within the similar range, where it will be much easier for us to come out with something. Like the step to go from tough to ABS, that's a really big one. You have to change the chamber, you're printing at a completely different temperature. It's a lot of tuning, and of course the hardware component. But now that we have that, like you said, we showed it with the first machine. We did PLA and tough first, and then very fast follow was PETG, because it was easier for us to do, because we already, it prints at a little bit higher chamber temperature, but it was not as big of a leap. So I guess what I'm saying, I can't really comment on the materials that we have in the pipeline, but I can tell you that it is now easier to tune for some of them, because we already tackled this
So do we have a date for that?
Let me put it this way, there will be more materials coming out this year.
There you go. So that's
that's
VP of product committing to a date. Any more questions, Saba?
Yeah, the last question that I saw was, is there a cart, or will there be a cart for Method?
Oh, is there a cart for Method? Actually, funny you ask. I swear that this was not planted in there, but it's actually what we have right here. If you go right now to the store, and maybe Mateo in the camera can pan a little bit, we have the cart here. So the cart is a great add-on for the machine I have. I'm happy to say that I have a couple of Methods in my desk, and one of the carts. And yeah, so it's quite a nice design from our product designer, Vishnu. And basically it has a top drawer and 2 bottom drawers right here to store the filament in there. And of course, you're able to hold the printer nicely, and it's also rolling, which is great. So yeah, we have the cart. I'm not sure about the price point. I think it's like you would check.
$19.95, I think.
Yeah, maybe check it on the website. It's also available on e-commerce today, but it's on the store. If you go to the Method page and then go to the Method store, you will be able to see it. If you have any of those questions specifically, I think that there's actually a follow-up from our sales team. So anybody who would like to have a quote, please do email us. You're seeing that email in the screen. It's hello@makerbot.com. And we'll be sure to send you a quote for anything that you want, any of the specific either material purchases, Method purchases, or just more information about the system. But yeah, so I think that sort of sums it up. And thanks, Johan. Thanks for joining us today. Thank all of you guys for joining. Stay tuned for the next one. I think it's always happy. For me at least, it's a great day to work with you and show you what we're doing here at MakerBot. So Feel free to add more comments. Let us know if you want to hear more about certain things or specific questions that you might have that we would be able to answer in the next coming webinars. And with that, thanks again. Reach out, hello@MakerBot. Any questions and comments, and thanks for Alison and Mateo back behind the cameras, and we'll see you next time.